Friends, I had explained to you the concepts of Rx and Ry regions in my last class. Today I'll tell you how to use that knowledge to evaluate some double integrals. Before we start this lecture, I would like to tell you that you must once again polish your geometry skills. You must be able to plot the curves whose equations are provided. At the lower level, the commonly occurring curves will be straight lines, circles, ellipses, hyperbolas, and parabolas. Of course, when we go to higher concepts, we may have to also learn a little bit about polar curves, which are plotted in a different reference frame. Anyway, the focus now is how to use the knowledge of Rx and Ry regions to evaluate some double integrals. My first problem is where I have to double integrate the function x squared plus y squared over R, where R is a triangular region having vertices at 0, 0, 1, 0, 0. So let me show you how exactly this region looks like before we analyze whether it's an Rx region or an Ry region, and then fix the limits. So let us draw the reference frame and show the three corners of the triangle. This is the origin. 1, 0 will be on the x-axis, 0, 1 on the y-axis, and this is the region of integration. So I'll call it R first. Now, whenever you want to do a double integration problem, you must have sufficient information about the region and the boundaries. So here, let us write the equations of the boundaries. Now let us take this boundary. That's the y-axis whose equation is x is equal to 0. This is the x-axis whose equation is y is equal to 0. And that's a straight line whose equation can easily be written as x plus y is equal to 1. Now this is the region that has to be analyzed. So I can see this region in two ways. If I want to see this region as an Rx region, this is what I'll be doing. I'll once again mark my corners. And I will I'll try to fix this region between two vertical lines. So this region I'm trying to fix within two vertical lines, and I observe the lower curve and the upper curve. This lower curve, this upper curve do not intersect anywhere in between. That's exactly what we need about an Rx region. So let me now write all the details. X is equal to 0 to x is equal to 1. Those will be the constant limits. Y is equal to 0 to y is equal to 1 minus x. This is coming from this equation, writing y as a function of x. So I can write this region as Rx described by x is equal to 0, x is equal to 1. This is the lower limit of x, this is the upper limit of x, which should be constants. Then coming to the y limits, the lower curve will offer the lower limit and the upper curve will offer the upper limit. So y is equal to 0, y is equal to 1. Therefore, when I want to evaluate this double integral using the Rx rule, then I'll have x is equal to 0 to 1, y is equal to 0 to 1 minus x, the function x squared plus y squared, and this dA, the area element, which was explained in the previous lecture, should be dy dx. That is, when the inner limits are functions of x, the order of integration will be dy dx. With respect to y first, with respect to x next. So let us see how to evaluate this. So continuing from here, I'm going to first begin my integration with respect to y. 0 to 1. The integration of x squared with respect to y is x squared y. Then we have y cubed by 3. The limits of y are 0 to 1 minus x dx. So let us submit the limits. Lower limit will not contribute anything, but when we substitute the upper limit 1 minus x for y, I get x squared into 1 minus x plus 1 minus x whole cube divided by 3 dx. This needs a little bit of simplification. I will not touch this because this is ready for integration, but here I'll have to open it up. X squared minus x cubed plus 1 minus x whole cube divided by 3 dx. This is straightforward. The integration of x squared is x cubed by 3. The integration of x cubed is x power 4 by 4. The integration of 1 minus x whole cube will be 1 minus x to the power of 4 by 3 times minus 4. You know, this minus sign is important because of the minus sign there, from 0 to 1. Of course, you have an option of expanding 1 minus x whole cube, but that is avoidable because it consumes a lot of space. So let me submit the limits now. I get 1 by 3 minus 1 by 4 minus 1 by 12 times 1 minus 1 is 0. But the lower limit is extremely important with respect to the third term because it produces a non-zero value. First two values will be 0. So we get minus 1 by 12. So we are now having 1 by 3 minus 1 by 4 plus 1 by 12. So let's take the LCM. We have 4 minus 3 plus 1. That is 5 minus 3 is 2 upon 12 or 1 upon 6. Well, the integration is definitely important because that gives us a final output. But I want you to understand the process that I have used to evaluate this integral. So this is how you can evaluate this double integral over this region as an Rx region. So the thing that I'm going to explain now is, can we also see the same region as Ry and still get the output? So let me explain to you. Okay, now I'm going to see the same region as Ry. And let us first of all see whether it can be expressed as an Ry region. Now, what is the principle of Ry? The principle of Ry is to fix the region within horizontal lines. So let's look at the original diagram, which is already labeled, and I'm trying to see the same region within horizontal lines. This is one horizontal, this is the other horizontal. So let us write the equations. Y is equal to 0, y is equal to 1. Now when it comes to the x limits, this is the left boundary and this is the right boundary. I'll just write for your convenience L and R. Now, the question that we have to ask ourselves is, between these two horizontal lines, are the left and right curves crossing each other or not? So you can see that the left and the right curves are not intersecting anywhere in between. So that will make it a perfect RY region. So let us write the equations of this left boundary. It is x is equal to 0, and this is x is equal to 1 minus y coming from here. So you are doing exactly the opposite of what you did in the case of Rx. In Rx, you fix within vertical lines. In Ry, you fix within horizontal lines. So let us write the description of this Ry region. Y limits first start with y is equal to 0, then go upwards and it will be y is equal to 1. So these are the two fixed lines, horizontal lines. Now comes the x limits. Begin with the left limit, x is equal to 0, then go to the right, x is equal to 1 minus 1. So with this, we can now write I is equal to 0 to 1, 0 to 1 minus y, x squared plus y squared. And because these are the limits of x, it will be dx first. Because these are the limits for y, it will be dy next. I hope it's clear. 0 to 1. The integration of x squared, because we are initiating the integration with respect to x, will be x cubed by 3 plus y square x. 0 to 1 minus y dy. Submit the limits in place of x. You get 1 minus x whole cube by 3, rather 1 minus y whole cube by 3 plus y square into 1 minus y dy, with the lower limit contributing nothing. Now it is this function that we will have to integrate again. As I explained earlier, you don't have to expand this because it's ready for integration, but this needs a little bit of expansion. So you get all these things naturally. Let me integrate this. 1 minus y power 4 by 3 times minus 4 plus y cube by 3 minus y power 4 by 4 from 0 to 1. So when you submit the upper limit, this produces a 0 plus 1 by 3 minus 1 by 4 minus. This 0 is a very important, it plays an important role now with respect to the first term here. We get minus 1 by 12 plus 0 minus 0. And it ends exactly the same way we did the previous Rx way, and this will give us 1 by 6. So the output remains the same, irrespective of whether you analyze the region as Rx or Ry. And we can also see I have consumed the same amount of, or same number of steps, because the function x square plus y square is symmetric. And even the region that is on the board, we can see that it looks very similar whether we see as Rx or Ry. But if there was asymmetry in the region or the function, then one of them would definitely be longer. So all this you will learn in due course. This is my second example where I have chosen to see that this is not both Rx and Ry. So we will decide after drawing the graphs of both the equations. We will consider seeing first as an Rx region, but in case the region does not meet the criteria of an Rx region, then we'll try to put it as an R variable, right? Now we all know y square is equal to x is a horizontal parabola. And this is a straight line which can be easily understood if you write it in the intercept form. So it has got a positive intercept of 2 units and a positive y-intercept of 2 units. Okay? So clearly it's not passing through the origin because there's a constant term. So let me put it on the plane and check which shape. So y square is equal to x. We'll have an upper branch as well as a lower branch. And then comes the straight line, x by 2 plus y by 2 is equal to 1. So mark 2 units on the x-axis. Mark 2 units on the positive y-axis. So this would be 2, 0. That would be 0, 2. Join. Don't stop there. Extend till it meets the lower branch of the parabola. So the problem is extremely clear. The region between the straight line and the parabola, right? So I will draw the parabola, and I draw the straight line, and then I shade my region. Now you have to find the points of intersection. These points are not obvious. These points are not obvious. So let us solve. So we'll have to solve y square is equal to x and y is equal to 2 minus x. Or let us write it as x is equal to 2 minus 1. That will be more convenient. So when I insert x is equal to 2 minus y in this equation, I'll get y square is equal to 2 minus y, giving y square plus y minus 2 is equal to 0. There are two solutions, y is equal to minus 2 and y is equal to. You can either get this by hand factorization or you can use a calculator. Right. For these y values, what are the corresponding x values? We can take either this equation or you can take this equation. Suppose I take this equation. So insert in x is equal to y square. I'll get for y is equal to minus 2, x would be minus 2 whole square, which is 4. I'll get for y is equal to 1, x is equal to 1 square, which is 1. So, from y is equal to minus 2 and x is equal to 4, I get one intersection point as 4 comma minus 2. So, you can easily sense that this is in the fourth quadrant, which means this is the point 4 comma minus 2. 4 comma minus 2. Then for y is equal to 1, x is equal to 1. So we can form one more ordered pair, x is equal to 1, y is equal to 1. This would be in the first quadrant. So no confusion, this has to be the point 1 comma. Now, with this region, let us see whether it is an Rx or an Ry region. If you think it's an Rx region, you must draw vertical lines. Where do you draw the vertical lines? You must draw the vertical lines at the leftmost point of the region, which is this, and one vertical line here at the extreme right position. So consider the leftmost point, rightmost point. Imagine you're drawing vertical lines. Yes, we have drawn, let's say. For the sake of understanding, let me put it. So this is the vertical line, this is the vertical line. Now I'm searching for what? I'm seeing whether there are any intersections in between these two vertical lines. Yes, there is an intersection there, which means it's prohibited under Rx. So it is not an Rx region. Once again, between vertical lines, if you find the curves are intersecting anywhere in between, don't call it Rx. So which means I will have to forget Rx for this problem and see if it's an RY region. So I will just wipe out this vertical line that I just drew and see this region within a horizontal framework. So let me draw one horizontal line there and the second horizontal line here. So where am I drawing my horizontal lines? At the bottommost point and the topmost point. Where do you draw vertical lines for Rx? You draw them at the leftmost and the rightmost points. Now what you have to do is observe whether between these two horizontal lines, this left curve and that right curve have any intersections in between. So between these two horizontals, I don't see this left curve and that right curve intersecting anywhere. So this is definitely an RY region. Now let us write the equations. For the RY region, the lower y will be y is equal to -2. This upper y will be y is equal to 1. So let me describe this as Ry. Y is equal to -2 to y is equal to 1, semicolon. Now comes the x limits. Go to the left curve, write that as x as a function of y. And don't forget this is the parabola. And the parabola equation is x is equal to y squared. So I write x is equal to y squared. And then the right curve is a straight line whose equation is x plus y is equal to 2. But you must write that like this, x as a function of y. So the x limits will be left curve first, x is equal to y squared, and x is equal to 2 minus 1. So this region is not so simple. The region between a horizontal parabola and a straight line like x plus y is equal to 2 will enclose an RY region and not an Rx region. I hope you understood this. Let me take an example where the region cannot be classified as Rx or Ry. Then what should be the strategy? Let us talk about that after this.